you multiply that reaction rate by the energy per fission, you should be able to calculate the total thermal energy generated here. But we have to stop a little bit with this equation to define some terms and some unknown variables here, because this is very tricky equations that we need to use carefully so we can convert everything into energy. So let's write down the equation one by one, and let's define the unknown terms here. So we're still under neutron flux. So we have, I'm going to start with the Cartesian coordinate formula. So we have phi c naught cosine pi x over a e cosine pi y over be times cosine pi z over ce. Let me draw that cubical shape of the reactor. That's the shape of the reactor. It's Cartesian coordinate system as much as I can. Okay, roughly. Then the core center, this is your core. The core center is the center point of that geometry. So that's going to be x, it's going to be y, that's going to be z. So the point 0, 0, 0 is the center geometry, the center point of the geometry here. A is the side length in the x direction. B is the side length in the y direction, and C is the height of that reactor shape. So, which means that x can it change all the way from minus a over 2 all the way to the a over 2. Since this is the center point, so I can go from minus a over 2 to a over 2. Y can go from minus b over 2 all the way to the b over 2. C can go from minus c over 2 all the way to the c over 2. Okay, so A, B, C are the three dimensions: x, length, side, and height, length, width, and height of that reactor shape. So x, y, z, x, y, z, these are the variables. So you pick the point inside the reactor, find the coordinates x, y, z for the reactor. This is where you're going to substitute here to calculate the neutron flux, which means that neutron flux we are calculating is function of x, y, and z. So, for example, if I pick up the center point of the core, it's going to be cosine x of the center point is 0, cosine 0 is 1, cosine 0 is 1, cosine 0 is 1. So at the core center, the neutron flux phi at 0, 0, 0 is actually phi c naught. So phi c naught now is defined as the neutron flux at core center. Then we know that cosine can go from 1 to minus 1, which means that if you change the center point to any other location, this will be a fraction, this will be a fraction, this will be a fraction, which means that this is end up to be a fraction, which means that you are a fraction of the phi c naught, which is telling me that phi c naught is actually also the maximum neutron flux in the core. So you want to define phi c naught as the maximum neutron flux, it's okay. If you want to define that the core center neutron flux, it's still okay. But mathematically, it is still the maximum neutron flux in the core. Okay, so that's the definition of phi c naught. Then we defined x, y, z, right? Pi is pi. Then we have AE, BE, CE. But in the geometry here, I have A, B, and C. Why we have AE, BE, and CE? So when you look back to this diagram here, this is the physical boundary of the reactor. That's a solid boundary of the reactor, okay? We know that neutrons does not stop by physical boundaries. They penetrate, they diffuse, they can leak out, which means that according to different theories, diffusion theory or the transport theory, neutrons, but we stick more to this because we drove this equation from the diffusion equation. Neutrons cannot be physically stopped by the physical boundary of the reactor. They will leak outside. They will extend to the outside of the reactor core. And this is what I'm presenting here with that dashed line. So that pinky color thing is the physical boundary of the reactor, while the dashed line is experience or expressing the extension of the neutrons leaking out the physical boundary of the reactor. So the distance that neutrons can extend outside the physical boundary, we call that the extrapolated or the extrapolation distance. And that's what we define by D, or some reference books, we give that the letter E, either one. Which means that we have, when we talk about neutrons, and these are the equation for neutron flux, we have to consider that extrapolation distance in the equation, which is telling me that if this is your physical boundary, I know that there is a dashed line extending from all direction, like envelope, covering the whole reactor from all direction, and we assume that the extension is uniform in all direction. So if the physical dimension of the reactor here is A, I know that dashed line here should be called AE, and this distance for the dashed line will be BE, and that height of the reactor will be CE, where E is considering that extension of the dashed line from all direction, which is telling me that AE, which is the extrapolated length of the reactor, should be equal to the physical boundary of the reactor A, in addition to the dashed line will extend from this side, will extend from this side in the x direction, which means that it's going to add 2D into the equation. Okay? Now, what about BE? It's the extrapolated width. So this will be the actual width of the reactor plus double the extrapolation distance. There is one side here and one additional side here. When I do the extrapolated height of the reactor, will be the physical height of the reactor in addition to double the extrapolation distance. Again, do you want to call D or E? Both are correct, depending on the reference book you are dealing with. Okay, so this is very important to consider when we do the analysis here. If the extrapolation distance, if extrapolation length or distance is ignored, if stated in the problem, it's telling me that D or E will equal 0, which means that the extrapolation distance will equal the physical length of the reactor. The extrapolated width will equal to the physical width of the reactor. The extrapolated height will equal the physical height of the reactor, and that would simplify the problem a little bit. If not, you have to consider adding this distance to calculate AE, BE, CE, so you can go back to this equation and get the right answer for the neutron flux distribution at a given location. Okay? So that's for the cubical reactor. Now let's jump to the cylindrical reactor shape, which is, let's do the spherical one first, because cylindrical is the one that we're going to spend most of the time dealing with. So let's do the spherical reactor. How the equation looks like: the phi C naught divided by pi R over RE times sine pi R over R capital E. That's the equation that given in the table. This is a spherical reactor. Okay? So that's the core center, right? This is the variable R that extends from R equal 0 all the way to the physical boundary of the reactor, correct? What we call that radius here, that's what we call R capital. But we know that neutrons could actually extend beyond the physical boundary of the reactor. So I'm going to add an extrapolation length, that distance here, you call it D, you call it E, which means that this will be the RE, and RE should equal the physical radius plus the extrapolation distance. If you want to calculate the extrapolated diameter, this will be double the radius plus double the extrapolation distance, because if you talk about diameter, you have to add that extrapolation length from one side here and one side here. So now that explains what RE is. Pi is pi. We did talk about phi c naught. That's the neutron flux at the core center, or that's the maximum neutron flux. And R is the variable. This is variable. So if you want to calculate the neutron flux here, find the value of R, substitute into the equation. So this is the equation to calculate the neutron flux, and there is only one variable in this equation because the geometry of the reactor is a sphere, so it's only a function of R. Okay? Now, going to the cylindrical one, which is the one that we're going to deal with most of the time. So I have a cylindrical reactor. Let me actually draw the center line of the core. Now, this is the core center. How many variables we have? We have R, then we have Z, and the point 0 and 0 is located at the core center here. Okay, now let's look to the physical boundaries of the reactor. This is the, let me draw this. This is the physical radius of the reactor. We're going to call that R. This is the physical height of the reactor. We're going to call that H. But we know that neutron flux will extend outside the physical boundary of the reactor, as if I'm creating an envelope of a dashed line that's surrounding the whole reactor. So I know now there is an extra radius here that's called the RE. What is that distance is D or E, right? Then I will have a new height that's considering the distance between that dashed line and the physical boundary. I'm going to call that actually HE. Okay. Now I can relate RE is equal R plus 1 extrapolation distance. And the height, extrapolated height, equal the physical height plus, now if I talk about the height, I add that distance twice, so that's going to be 2D or 2E. Okay, now let's write down the equation. So the equation is phi c naught, then I will do cosine pi z over HE times J naught times 2.405 R over RE, and that's the equation. So this is a neutron flux as function of two variables, R and Z. So R and Z, or Z and R, whatever you want, doesn't matter. Phi as function of X, Y is the same as phi of function of Y and X. Okay, we did define HE and RE. These are the extrapolated or the extrapolation dimensions, right? R and Z, these are the variables. This is constant, this is constant. Now, phi c naught is the neutron flux at the core center, or the maximum neutron flux as defined in the other equation. What's very important for this equation actually is looking to the distribution of the neutron flux. So we have two-dimension distribution. We have one in the R direction, which is presented by that J naught function, and we have one in the Z direction presented by the cosine function. Okay, so let me rearrange the equation and look to that distribution, because it's very important to understand the neutron flux distribution in the cylindrical reactor core. So, and I will convert that three-dimension drawing into two-dimension drawing to make things more easy to understand. So I will draw the two-dimension reactor. Here is the core center. This is the 0.00. This is the coordinate R, which is here. And this is the coordinate Z, starting from that point. This is R capital. This is H capital. Then I'm going to draw the dash line surrounding again. It's always assumed that the extrapolation distance is the same from all direction, but just want to make things clear here. So this is RE, and this is actually going to be HE, right? Okay, now let's write down the equation. Phi as a function of R and Z is equal phi C naught. I'm just going to rearrange the equation. 2.405 R over RE times cosine pi Z over HE. Okay. Phi C naught is the maximum neutron flux in the core, or that's the core center neutron flux. That's constant. That's value. Then I have J naught. What is J naught? J naught is actually a Bessel function of order 0. Let me show you mathematically how it looks like. Bessel function of order 0 is simply a cyclic function. This is J naught. This is order 0 Bessel function. This is order 1. This is order 2. This is order 3. We only deal with order 0 Bessel function. If you look to the first cycle or half cycle of that Bessel function, it looks like exactly as a cosine function. So mathematically, it looks like a cosine function. Starting from 1 goes to 0 in that first period here. So graphically, if you look to the Bessel function plot, which is function of R, and the cosine function plot, which is function of Z, this is the variation of the function with Z. This is the variation of function with R. We just plotted the first half, right? They looks like the same. That's the cosine function distribution. That's the Bessel function distribution. So when we look vertically, we look into the cosine distribution as shown here. That's function of Z. When we look horizontally, we look to the Bessel function, which looks like a cosine function in plotting, right? Okay. Now, always, or in most cases, we're looking for the vertical axial distribution of everything. We're looking to neutron flux axial distribution. We're looking for the heat generation axial distribution. We'll look to the flow rate axial direction. So usually in the axial direction, that's what we are interested in. So let's focus more on the axial direction, okay? So axial direction means that the distribution of the neutron flux is a cosine function, okay? So let's assume that I'm gonna pick a value of coordinate R, which is the center line here. So assume we are picking R equals 0. So I'm looking for a fill rod that's located at the core center. So assume we have a fill rod located here, and I would like to look into the neutron flux distribution surrounding that fill rod. Keep in mind, fill rods will physically stop at the physical boundary of the reactor, while neutrons are not. Neutrons can go all the way to the dashed line. Fill rod cannot exceed the physical boundary of the reactor. So that's my fill rod here. This is at R equals 0. So if I put R equals 0, I'm looking for phi C node, J node of 0, right? Times cosine pi Z over HE. Assume I want to plot that function here. Now, where are we going to get that Bessel function? If you use Excel, you can calculate Bessel function, but also we have table for that Bessel function. That table will be provided on the course web page. So this is 0 zero order Bessel function. I think I mentioned first order. No, it's actually zero order. J node, it's zero order Bessel function. And that's what we need for this equation. I wrote it down, J node or G0. I think, yeah, okay. J0 of any value, that's a column here. And the value is inside here. So that value X, R, or whatever is the value inside these parentheses. Then J node is what you get from the second column. For example, what is the value inside the parentheses here? It is 0. So I'm looking for J node of 0. So for 0, J node of 0 is 1. The more you move away from the core center, what's happening to the value of R? R starts with 0 here, but R is a variable, it's going to increase. So R is going to go up. So the value inside the parentheses will go up. The more the value between the parentheses goes up, the value of J node actually goes down, which is telling me that at the core center, J node of 0, this here is 1. That's max, correct? That's max. So I'm going to end up having the core center neutron flux times cosine pi z over HE. Now, I can put z equals 0, right? I can put z equal whatever. I can change z all the way from minus HE over 2 all the way to the HE over 2. You said we cannot go for HE. I said that's for the fuel. This equation is for neutron flux. A neutron flux can go extend beyond the physical boundary of the reactor. If you do that, you will find the following. What is phi c naught called? That's called the amplitude of the cosine function. This is when you put z equals 0, cosine 0 is 1, you get this at the z equals 0. So you will find that the neutron flux, if you plot this function, you will find that neutron flux looks like this. Neutron flux reaches 0 at the dashed line because you put z equal HE over 2, HE over 2, HE will cancel out, cosine pi over 2 will be 0, times phi c naught is going to be 0, I got 0. You go all the way at the center, z is equal 0, you got that phi c naught. So this amplitude here, this height here of that curve is phi c naught. And I end up having 0 at the dashed line. That's the profile of the neutron flux distribution for a fuel rod at the core center. What if the fuel rod is not at the core center? Let's shift it a little bit. Let's assume that I picked up the fuel rod here. Let's assume that's my fuel rod. Just for demo here. Do you know that coordinate value R? Yes, I have a value. I'm going to put that value here. That's not going to be 0 anymore. It's going to be 2.405 times that value R divided by RE, which is a constant value. So I will have J node of a number. I will go to that Bessel function here. I will find what this number is. I will find the corresponding J node of that number. It's going to be a fraction. So I'm going to end up having phi c node times a fraction times the same curve. So what happened here is the amplitude of that cosine function shrink it down, contracted by that coefficient J node of 2.405 times the value of R divided by RE. This is the contraction factor that you have here. So what's going to happen is the amplitude of the cosine function shrink it down by that contraction factor. So I will have the same profile curve, but the amplitude of that curve is slightly less. And shrink it by that J node 2.405. So this value here, it's phi c node times that fraction. So the curve get compacted a little bit, ending up 0 at the dashed line here. The more you go to the right, the amplitude keeps shrinking, 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 until you reach actually to that, theoretically, the fill rod at the physical boundary of the reactor, this will be all zeros, right? Is nothing. Okay? So keep that in mind. The same situation happened on the left side. So we are using the symmetry of the reactor, so you don't have to do that. So the point is, phi as a function of R and Z can be written as phi C naught, J naught 2.405 times R divided by RE times cosine pi Z over HE. Okay? I can combine these together because this is presenting the amplitude at any specific location R. This will be a fraction. This will be the maximum neutron flux. So I can write down the equation as follow. Phi only C. So the subscript node is for the core center. This is the amplitude away from the core center. So this is phi C node, correct? This is phi C node time a fraction. This is what I call phi C only. So that's my phi C times cosine pi Z over HE. Please be careful when you deal with the two forms of the equation. This is the neutron flux amplitude at the core center times J naught. This, a combination of these two together. So this is the amplitude of the cosine function for the neutron flux, not at the core center. It's away from the core center. So both equations are correct. Depending on the given information you can use. And you know the relationship between phi C and phi C naught is that contraction factor that you calculate based on the location of the fill rod. This is very crucial to understand how to do the distribution of the neutron flux. I hope that explained that very carefully here, okay? And the reason we take that, because if I integrate that profile for the neutron flux, I can get the total neutron flux. Then you will be surprised. Actually, let's write down that. You guys remember we said we can calculate the reaction rate, right? From what? From N times sigma times what? Times the neutron flux. Then after I get that reaction rate, which is number of reactions per unit volume, per unit time. If I multiply that by 200 MeV times phi times N times sigma, this is what? This is MeV per fission, per reaction. If you multiply that, you're going to end up having actually MeV per second centimeter cube. What do we call that? MeV is energy. Energy per time is power. Power per unit volume, that's what we call it what? Volumetric heat generation. And this is how we're going to convert the neutron flux into Q triple prime or Q dot. You guys remember from the heat transfer basics? Q triple prime is a volumetric heat generation, or the volumetric thermal source strength, or heat generation per unit volume. Call it whatever you want. The unit is telling me that I can convert that reaction rate into heat generation. If I integrate the neutron flux, I can integrate the Q triple prime. You look to that. N is number density. That's a factor, constant. Sigma, tabulated value, right? 200 is constant. So the behavior of the neutron flux is matching the behavior of Q triple prime. So the distribution of the neutron flux is the same as the distribution of the volumetric heat generation. If I integrate the neutron heat flux, I can integrate the same profile for Q triple prime. I will get the total energy generated by a fill rod. And this is what would take us from not just the localized, remember, this is function of R and Z. This will be the same function of R and Z. If this is function of X, Y, and Z, this will be function of, this is localized heat generation. This is localized thermal strength source. That's localized value. But if you integrate, you can get the overall, you can get the volume, per unit volume, you can get the total energy. And we're going to talk about this in details. But again, this is why it is very important to understand the neutron flux distribution, because the heat generation will follow the same distribution, and we will do multiple of aside processes for integration to get the total energy. So I hope you guys follow that very carefully here with the neutral flux distribution.